when we approached the general question of classification or regression, we talk about different machine learning approaches to a problem, right? And different approaches, well, we sort of came up with three different types, right? One is instance-based, which is your k nearest neighbors, for example. One is formula-based, so you write a formula, and this formula divides the space or draws a line or hyperplane. So that's a linear model. And the last one we're going to talk about, well, almost next to the last one. There is also one probabilistic, which we're going to talk about next time or time after next. But what we're going to talk about is a big, huge chunk of machine learning methods, which are rule-based. And when I say rule-based, I mostly mean trees, right? So let's talk about decision trees today. And a decision tree, hope you see the tree with a good resolution, because I'm going to draw on it and write on it. So a decision tree divides your data and hopefully some new data and validation data into leaves, right? So you have leaves, you have branches, and you have a root. And it's rule-based, right? So you write a rule. So this is, again, a very commonly used data set, which is called iris data set, and it's about classifying iris flowers into three classes, right, according to their species. One is setosa, one is versicolor, and one is virginica. So there are three types of flowers, and you want to classify. So what can you do? You can write. You have your features such as petal length, right, or petal width, or sepal length, or sepal width. So it's all like a shape of the flower defined, right? So width, length, stuff like components of the flower. And you can write. You can find the closest one, right? You can do k nearest neighbors, or you can do linear function, right? So you can use a neural network, for example, right? The input and output the classification, use softmax, stuff like that. What you can also do is you can write rules, right? So let's write the first rule. The first rule, if petal length is less than 245 centimeters, right? So then one is true, one is false. And if it's true, then you can sort of see that we already separated the whole class. So we have three classes and the whole class is separated, right? So this rule separates one class from both the other classes. It's very good. Then you can find another rule for the rest, right? And this almost separates them. So there's 49 points from versicolor class, 5 points from virginica class. Here's 1 point from versicolor and 45 from virginica. So you can sort of ended up here, and this would be a nice tree, right? So you sort of divided them just using two rules, right? Not some complex formula with neural networks, not by calculating distances. You just have two rules for two features, all right? So two rules, two features, very nice, and it's already a good classifier. What is this? Well, this is overfitting, right? So you can come up with more rules. So you can get a leaf where only 1 point is presented. And we'll see a graphic representation of an overfitting problem with trees, but here you can sort of see what is overfitting, right? It's when you go deeper than you should have. Now, this is a general picture of a tree. There are some advantages to a tree. And the most commonly mentioned one is interpretability. Interpretability means, okay, you understand the rules, right? So it's not some complex formula. Well, distance in high dimensional space is also kind of strangely defined.
А можно небольшой вопрос? Вот value — это количество точек?
Yeah.
Окей, спасибо.
So this is a vector value of class distribution. Yeah. So number of, so the initial data set had 150 points, right? This is the initial data, and it gets, so this is a training data. This is a trained data set, and it gets separated. Just a second, I'll put on a better light. Look like a heavenly figure. That's nice. Okay. So let's go into advantages of decision trees. The first one mentioned is always interpretability, because, well, you can sort of see how your algorithm works. Now, the problem is most of modern tree-based algorithms are ensemble algorithms, and they're not as easily interpretable, especially when we get to a gradient boosted decision trees. Right, next lecture would be on trees ensemble, and interpretability kind of loses there. So you can talk about interpretability when you talk about one tree, but when you have an ensemble of trees, you have a random forest or a gradient boosted forest. Now, interpretability is something that you cannot enjoy. So yeah, almost no need for pre-processing. Absolutely right. So you don't actually need to separate categorical features, right? You don't need to go one-hot encoding. You don't need to scale, because your rules are thresholds, right? So when you have a numerical feature, you can say, okay, this is a threshold. And it doesn't matter whether a feature is scaled or not, correct? You can actually perform that experiment. You can have a data set, you can scale features and not scale features, apply tree, and you see you will arrive at the same exact result. Right, because it doesn't matter whether a feature is scaled or not. You just sort of a rule is a threshold. And with categorical features, well, you can just say if it's that category or not that category, right? So it's automatically one-hot encoded, sort of. And this goes for the third point. Resilience. Now, this is a complex point to explain. What do I mean when I say a network is resilient? Not a network, but a tree. Just a second, I'll move into the light as well. So when I say a tree is resilient rather than network, which is not resilient, I talk about a small variations in data. So a small variation in data, because of the complex structure, for example, of a neural network, can throw out the whole, like we talked about adversarial examples, right? When you change a picture a little bit, but then the output changes a lot. You cannot do that with trees, right? Trees separate. If tree is built well, then trees separate the space into a nicely looking sort of division, right, of subspaces. While neural network can be very convoluted and very strangely looking with trees, because you separate. So let's see if you have, okay, if we have a feature, just a second. If you have a feature space, right, x1, x2, then every rule separates your subspace by horizontal or vertical lines, right? So this is a rule. We take x1 is greater than this value, a. Right, so, and this is nicely looking, and it's more resilient to minute changes. So, for example, in neural network, when you talk about space, neural network it sort of looks like this, right? So if I have, well, let's say 2 features, then the space of a neural network is something like this. And when you go a little bit here, you can go from one decision to another decision to one decision to another decision. So this is not a resilient method. Окей.
Небольшой вопрос. А в чем тут отличие от KNN? Мы же там тоже делили на такие участки.
KNN is also a resilient method, yes. Okay. So both trees and KNN are both resilient. Linear models are, generally speaking, not, especially deep neural networks. I think KNN is the most resilient method, but it's also not very good in terms of performance. Okay. Now, the question is, how do we build a tree? Right? If you have a tree, it's easy to understand how you decide, right? But how do we build the tree? Well, we need a step-by-step solution, and for that we need some sort of metric. So let's say we try to find a best rule, a best division for a subsample, right? So let's say we arrive at some point in the tree, right? So here we already divided somehow, and we want, so here I have some sort of, I don't know, let's say again, 3 classes. And I want to find the best rule for division. What will I do? Well, I can just go through every rule, every possible rule, right? So here for n, well, if n is the number of points, well, n is 80, right? How many features? Let's say, well, for vesicular, for iris flowers, there are just 4 features, I think, right? So you only have to check kn thresholds, well, actually even less than kn, right? Because if you have n points, right, there are only n minus 1 rules because you need to separate points, right? Okay, n minus 1. So you have k features, n minus 1 thresholds, and this is just not a very big number, right? So it's 80 and 4 is 240, right? No, 320. Not a big number to check. It gets higher. There are some techniques that we can talk about how to speed up trees, but the general rule is you sort of have to check every possible rule and see which rule gives you the best outcome. And what do I say what do I mean when I say the best outcome? I mean best information gain. An information gain is a general term for a tree separation metric. I lost the chat. Just a second. Oh, good. So an information gain, you have a separation, and you separate your initial X node points, right, into X right and X left. This is a point, so this is a sort of vector, basically, of your points. So let's say this is 0, 30, 50, right? And ideally, this is 0, 30, 0, and this is 0, 0, 50, right? But it can be different. So this is, of course, this just the size, and this is not information, strangely, but impurity. Impurity. So this I and this I are different. This is just how it is. So this I is information gain, but what you calculate is the loss of impurity. Right? So you get the lower the resulting impurities are in the leaves, the higher the information gain. Correct? Right? And this goes down because of the minus. This goes up. Correct? So we want to lower impurities. What are impurities? There are 3 main impurity functions there are. And the first one is very easy. So let's say I have 3 classes. I have, so here I have 50, right? How do I calculate impurity from that vector? What is the easiest one? Any ideas? Come on, there are 40 people. Some should have ideas. There are not 40 people. Where are the rest of you guys? Why are there only 20 people in the conference? Okay, I'm going to talk to your supervisor about that. But still, I see 5 people. I think those are engaged one at least. So any ideas? What is the most obvious thing you should lower?
Ну, количество точек, которые находятся в разных классах.
Sure. Or you can say an error, right? So because it's a classification algorithm. So let's say we finish there, right? Let's say this is the last separation. then for those 60 points, 10 points would be wrongly classified, right? So this is our error in sample in that particular leaf, correct? And we want the error to be as low as possible. Right, so if you want the error to be as low as possible, then this impurity can go as low as possible. Then this information gain is actually a loss in error. And this is our first impurity, a misclassification error. Easy to calculate again, right? If you have the majority class, right? So here's, let's put 10 here as well, and 50. So you have the majority class. This is your max, right? So this is 50 divided by the whole point, 70, right? And you -1 it, so 20 over 70. So this is your misclassification error. Or how many points will you misclassify if you classify by the majority class? Correct? Good. Okay. Why is this function bad? Why do we need more information gains? Well, the idea is very simple. We sort of try to create a intermediate separation by the final metric, right? So the final metric is correct. If we end up with errors zeros, right, in the leaves, we are pretty much done. This is a very good tree, correct? Now, the thing is, when we separate them in the beginning, maybe the first row or initial row or any intermediate rules should not aim at immediately lowering the end metric. A controversial idea, but it works. Because when we transition to another metric, okay, another metric, let's come up with this one. Again, you have a vector, right? And you want sort of this to be worse than this. So one is misclassification error, another one. Any ideas? Have you heard of entropy? Yes, good. Entropy, right? So entropy is best when everything is in one bucket, right? So if it's the worst entropy here would be, well, 70 is not actually divided by 3, but if everything is the same, right? If all classes are exactly the same, this is the worst entropy. And the best entropy is 0 when all belong to the same class. This is just a formula for entropy, right? P log P, correct? Minus, because log P is negative, right? So this is, again, P is just a probability of a class or a ratio of a class to the whole number of points. So this is from 0 to 1, right? So probability. So this is negative, right? That's not, it's minus, then it's positive value. And the lower it is, the better, right? Because it's, again, we want this to be as high as possible, sort of for one class. And if this, so a perfect situation, I'll just write probabilities, is 0, 0, 1, correct? And in this situation, so for first two classes, this is 0. So it's just 0 plus 0 plus 1 times logarithm of 1, 0. All right, so this is the best entropy, 0. When all points belong to the same class, it's 0. When it's not, then it's higher, right? And I think for 3 classes, it's somewhere around 220, 2.5, I don't remember. It's 1/3, 1/3, 1/3. We'll see, I think, an example. Now, who sees the problem with this function, for example? And it's a good function, it actually works very good. But there's one problem that brought up the transition from entropy to a next impurity. The next impurity is, and the final impurity that we actually mostly use when we build trees, is called Gini impurity. And actually, Gini impurity is the reason why all others are called impurities as well, because this is the most commonly used. So now entropy is also impurity, and misclassification error is also impurity because of that impurity. And Gini, named after a famous economist, Gini, Italian, I think, or Italian American. Gini impurity sort of looks like entropy, by the way, right? So it's just a p, but not times log p, but rather times 1 minus p, right? So again, we want this if everything is 0, 0, 1, right? Then this is 0, this is 0, and if it's 1, then this is 0, right? So the lowest Gini impurity is still 0, and the highest is when everything is equal. And now there is an interpretation of Gini impurity. An interpretation is stated like this. This is a probability of error if we will choose according to probabilities of classes, right? What am I talking about? Let's see. Let's say 3, 2, 5, right? So this is easy to put up with. Now, misclassification error is a probability of error if we choose the majority class, right? So a misclassification error here is 50%, correct? Right? If we always choose the third class, 5 points is correct, 5 points are not correct. Now a Gini criterion says, okay, let's not choose the majority class, but let's choose according to the probability of classes, right? So we have the probability of 3 by 10, 2 by 10, and 5 by 10, right? Or 0.3, 0.2, 0.5. Now, let's calculate the probability of error if we are going to choose by the probability. What is the probability of choosing the first class? 0.3. And what is the probability of us being incorrect? Well, 0.7, right? So the probability of us choosing the first class times the probability of at the point actually being in the wrong class, correct? So this is P times 1 minus P, right? So then 0.2 multiplied by, multiplied by 0.8 and 0.5 multiplied by 0.5. And you add them up and you get the Gini impurity. Now, if you look on the graph for Gini and entropy and misclassification error for binary classification, right? Let's say you have two classes, and this is a probability of one of them. So this is a probability of a majority class or a minority class, doesn't matter. So misclassification error and the all highest when this is 0.5, right? If the both classes are equally present. Now, if one class or the other class is just present, then it's 0, which is good. And actually, entropy here is higher. So the exact entropy is something like this. So it goes higher, but it's scaled, so you can see it doesn't matter how you scale it because you select, right? Well, you can scale the metric by the same number, but because you choose the maximum, right? The maximum information gain doesn't matter how you scale the metric. So just scale to approach Gini. And you can see here that both entropy and Gini criterion are quite close. Now, what is their main difference from the misclassification error? Well, the main difference is that it pushes towards separating classes from others. So here, what do I mean by that? And decrease from 0.5 to 0.4, right? And decrease from 0.9 to 0 is the same in misclassification error, correct? So if I go from here to here, or from here to here, it's the same. But in Gini criterion, if I go from 0.5 to 0.4, well, just a minute difference in information, right? But if I go from 0.1 to 0, it's a huge difference. So here is I cannot even draw it. It's very small. There's a small difference and there's a very big difference. So this is more prioritized, and this helps with classification. As in, if we use misclassification, the end metric, we'll sort of separate. We have a muddy separation, sort of fuzzy separation. But if we use Gini criterion or entropy, we will first classify the classes, try to classify the classes. And this was what happens in the initial tree that we looked, right? Here, Gini criterion, it prioritized a separation of the class. I'll see the example. And here is the example, right? So first one, we have binary classification. Why is not turning on? Okay. We have a binary classification. 40 points in one class, 40 points in. This is one separation, this is other separation, right? And here we have the whole class separated. So information gain with misclassification error is impurity. So this is the initial value, right? And it's separated in half. So 40 points here, 40 points here. And this is error, right? So error 10 points from 40 points is 0.5, 0.25. So this is just a formula, this formula. Right. Okay, now, oh, I see what I'm gonna, so they're the same, but both entropy, so here is entropy as impurity, right? It prioritizes this. So this is higher information gain in this case. And Gini criterion as well, they prioritize the second separation, right? So now back to the question. Okay, you have entropy. Why did we need to come up with Gini impurity? Because Gini impurity actually came up later than entropy. But why do we need Gini impurity if entropy and they actually both work the same? So why do we need Gini? Why do we prefer Gini impurity? While you think about it, I'll go get some water because I actually took a low amount. Okay, any ideas?
Возможно, логарифм сложнее считать.
Yes, correct. Right. You have to remember that machine learning algorithms, they all are calculated in a computer, right? On CPU or GPU. And when you have to calculate logarithm, it takes a long time. It takes a long time, right? This is where it steps from sigmoids to ReLUs. And this is why we step from entropy, where you have to calculate the logarithm, to Gini and Gini impurity, which is very simple. Okay, so let's talk about tree algorithms. This is sort of an evolution of algorithms. This was used like 20 years ago. This is 10 years ago. This is what we use now. If we talk about a single tree still, right? So we're talking about how to build a single tree. They are mostly built the same. A cart algorithm, which are disambiguated as a classification and regression trees, right? A cart algorithm is the one that introduced Gini impurity, So this was like a big step forward in terms of calculating time. But still they're the same. This is iterative dichotomizer 3. So iterative dichotomizer, right? We have a dichotomy and do it iteratively. And I think it's the same author of iterative dichotomizer 3, which was widely used, and C4 which is just a C. It doesn't mean anything. That's his words. I don't know. Maybe it does. Maybe it's a classifier. I think, well, I have no reason not to trust him. Just C. I have A, B, C, and this is a good algorithm. So it's C.1, all right? So stuff like that. They all sort of do the same thing. They're different various implementations and impurities, but sort of the same thing. So what is the algorithm? This is an end condition. If all objects in the node belong to the same class, then this is a leaf, and you mark it to the same class, and you say, okay, this is a leaf, and a leaf is a class versicolor, right? And this is a leaf. This is a leaf of a class set also. If not, find the threshold with the best information gain. Easy, right? Go through all thresholds, calculate information gain for every threshold, for every feature. Find the best information gain. There could be a situation where no information is to be gained, right? When every information gain you calculate is 0, or, well, it sort of cannot be negative, but 0. So you cannot gain any information. Then you should stop, right, and assign it with the majority class. So let's imagine this as after this node, we cannot gain any more information. So we stop, say, okay, this is still a versicolor leaf, right? Even though there are just 5 points of the other class, but still good enough. If we have information gain, we find the best information gain and separate by this threshold. And this is, we separate node into 2 nodes. That's it. And you call 1 in each node that you separate. Very easy to implement tree algorithm. Now, after you do all that, you get the tree. But since CART is a classification and regression tree, we need a regression impurity, right? So a classification CART uses Gini impurity, which we already sort of saw. This is the same as P. But we need something for regression. And we use deviance. A deviance is a pairwise sort of variance, but not from the middle value, but the pairwise. Okay, so the closer our points to each other, the lower the deviance, the higher the information gain, right? So let's just look at what the results look like. Left is classification, right is regression. Both CART. So the first thing you see is it does indeed separate, but by thresholds that are parallel, right, to features. Well, of course, right, because we take one feature and we separate by a plane that is perpendicular to that axis, right? So yeah, in terms of geometry, very understandable. Now, you can also see overfitting quite clearly, right? This is overfitting. Why? Well, it says this whole line is red. Well, it should be yellow, correct? If I get another point in a validation or test data that's on that line here, right, it should be yellow. It's not red by any means. So we created that whole subspace for one point here inside the margin. So we actually propagated that point, right? This is overfitting. And you can see sort of different. So here's, I think it's sepal width. Yeah, it's the same overfitting by sepal width. Okay. Now, regression. So here I only have one feature, right? X1, just one feature. So we can look at it. And I apply regression. So again, I choose rules, I separate space by those rules, and the leaf just has one number in it written. What number is it? It's the average of all values in that leaf, correct? This is the easiest thing to do. All right, so I end up, so here, for example, I have a leaf. Let me take a different color because it's red already. So I have a leaf here. I average those values, and I end up at the value of the leaf, this one. So this is how I build a tree. And here you can also clearly see overfitting, right? How do we fight overfitting? You should know by now. We already saw several examples.
Регуляризация.
Yes, we do regularization. And one easy way to regularize a tree is to just cut off the leaves, right? So let's say here, for example, I have a tree with depth of 5. So how many leaves is that if the depth is 5?
Ну, порядка 2 в 5.
Yeah. Which is?
2.
Yeah. Well, yeah, 32. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, yeah, 32 at some point. If I go to 2, this is just 4 leaves, right? And you can see them, they're green. So this is 1. This is the second one, a green one. This is the third one. This is the fourth one. But again, this is sort of a hard way to regularize, right? Because you lower the variance, sure, but you increase bias immensely, right? Because you cannot, now with a small tree, you cannot get any good classifier. So what can we do? Well, we use train, validate, test, of course. A train classifier is just a reminder. So you can change the tree depth, right? Sure, but it's a hard way. What's the other way? The other way is called pruning. Pruning is quite literally cutting branches of trees, right? It's a gardening term, which comes into machine learning because trees, garden, well, sure, pruning. So how do we prune? I will discuss just 2 ways, but there are many ways to prune a tree. The main 2 ways is minimum error pruning and cost complexity pruning. A minimum error pruning is easy. So you have your validation data set and you start cutting off leaves. And you cut them off until validation error does not increase, right? So while it stays the same, or even maybe it will get lower, you cut off leaves, right? So you take a leaf, you cut it off, see, okay, validation error, better, worse. If it's worse, don't cut the leaf off. If it's better, cut the leaf off. If it's the same, cut the leaf off, all the same. Easy, right? Cutting the leaves off, right? Now, there is such a thing as cost complexity pruning. Now, a cost complexity pruning introduces a penalty for a number of leaves, right? Sort of in the similar way we introduce a penalty for the square weights, right? When you have weight decay or L2 regularization or even L1 regularization, we introduce a penalty for weights, right? But now we can introduce the penalty for number of leaves, right? And or tree size in that case. So this is tree size. So our full error will be our error and some alpha times tree size, number of leaves, right? Usually M. Why? I mean, if we do minimum error, why to do a cost complexity pruning? Well, you have to remember that you can still overfit to a validation, right? So this sort of guarantees, this introduction of this new term sort of tries to guarantee that your validation will be close to your testing as well. Because you penalize the number of it, you penalize the size of the tree. So you sort of have to, it tries to push towards a guarantee towards not overfitting, right? So the smaller size is valuable by itself, right? Times alpha. But in terms of pruning, what does it mean? In terms of pruning, it means that, okay, you still build the tree the usual way, then you cut off the trees, cut off leaves, right? Cut off branches. But now, instead of looking whether the validation error is increased or decreased just at all, look, okay, if I cut off this branch, right? I lower the error by alpha. If the validation error is not increased by alpha or more, I should cut off the leaf, right? So if I gain alpha, but I do not lose alpha here, I should cut off the leaf. And that's cost complexity pruning. So you put a cost on tree complexity. Okay, now building a tree is costly, right? If you have many features and many points. So we talk about k times n minus 1, and if this is 100, this is 100, 10,000 thresholds, no problem. A computer is very fast. Well, what if it's 100, right, and it's 1,000,000? Well, you have to go through all the threshold, and remember, you have to do it for every node as well. Well, nodes get less, right? So when you separate, you have 1,000,000, 1,000K here. So here you only have, for example, 500K, and here 500K. So you have to go through less thresholds, fewer thresholds in the nodes. Still a huge number, right? And 1,000,000 points is sort of what we usually operate with. Or 10,000 to 1,000,000 points is still good for trees. How do we do that? Well, you have to speed up your algorithm. How do we speed up? So this is a calculation of a number. So a naive implementation is all or number of features, number of examples, right? Why? We have to go through every feature. We need to sort the examples by that feature, and we need to calculate the gain, which is usually done in number of examples, because you have to sum up how many in one class, how many in the other class. Hard. Now, how can you speed it up? Let's look at the techniques. First one, let's pre-sort by every feature and just keep the order, right? So let's say we pre-sort and we have a table with resin feature, and here are points. So x1, x2, x3, n. And instead of writing a feature number, we will just write the order in which this is on the line, right? So this is, for example, 10, and this is 1, and this is 100, right? So this is just the order in which these features are sorted. Well, let's write some values as well. So let's say 1, 0 here, 0, 1 here, and 10 here. So this is a feature value, but we can create a table where it's resorted and just keep the order, because it will not change, right? If we have that feature, sure, and you have points, and you have the order. If you take some points and say, okay, these points go to branch 1, and these points go to other branch, right? If you take those and you still have the order, even if it's not like in a row, right? If it's not sequential, the order still stands, right? This is still after that point, right? 7 is still higher than 3. So if you pick threshold, you do not actually pick a threshold. You pick a number from which you separate the points, right? So I say any point that's after 50 and any point before 50, right? And you can pre-sort it, and then you can only deal with those numbers. And it's easier. You don't have to calculate values. You have integer values, which is, again, easier to do and stuff like that. Now, binning. Binning is a way to lower the number of thresholds, right? So let's say we have 1,000,000 points and 1,000,000 thresholds. Well, I can say, okay, this is overkill, right? Let's have 1,000 thresholds. Let's only have like bin 1 with 1,000 points, bin 2, all right, with 1,000 points, so on. So now what you can do is you can actually write to all those points, you can write the bin number, right? Not the order, but just the bin number. All right, and say, okay, bin 1, 2, 3 go here, bin 3, well, 4, 5, 6 go here, right? So you only operate with bins. And you can pre-calculate the proportion of the classes as well, right? So if you have a bin with the proportion of the classes, you can say, okay, if I separate by that feature, then this goes here, this goes here. And it's easy to calculate. Now, histograms. Now, this is the main term for calculating class proportions, right? Why histograms? Well, if you have a leaf, right, you have class 0, 1, 2, and you have some proportions. Well, this is just a histogram, right? So this class is present, and this, for example, is not. This is a node, right, in a tree, and so on. So you want to calculate a histogram. Histogram gives you answer for a Gini criterion, right? So if you have a histogram, it's very easy to calculate the Gini criterion just by the formula. But how do you calculate the histogram? Well, you can do it sequentially, you can do it incrementally, right? So let's say you have a threshold, right? You have your points and say, okay, if I separate here, then I get some histogram here and some histogram here, right? Well, let's draw it differently, like this, right? Now, I need to check every threshold or every bin threshold. What can I do is, okay, the only thing that changes is this point, right? So this point belongs to some class. Let's say it's class 2, right? Which is, okay. So this means that I remove here, I remove point 2 and I add here. I do not have to recalculate the histogram, right? So you can incrementally calculate them, which is easier. And the last thing is you parallelize everything. Current state of the art tree algorithms, they work on GPUs, right? So there is a way to calculate all the binning, the histograms, everything on GPUs by tensor operations. So you can parallelize everything. What is more, you can actually send a node to a whole other computer, right? So, okay, I need to calculate that node, but it's isolated, right? If you have a tree, that this node actually doesn't have to know about this node at all, right? It's isolated. You can calculate Gini impurity, you can do histograms, everything. Everything is isolated in that node. So you can set that node to another PC, right? To another node on the server and make them calculated there. And then get the results back and compile the tree. So it's very easily parallelizable. Okay. Now, the last thing we're going to talk about today are different types of like strange trees. What am I talking about? The first one is oblivious decision tree. Okay, I have a message in chat. Repeat what is this question still stands, Yuri, about the binning? or is it clearer now? Yes, okay, let's go back. Binning. So when you have a feature, right, with some values, you need to check out every threshold, right? And if there's a million points, right? So here's the number of points. There's a million minus one thresholds. Binning is basically getting rid of all thresholds and just saying, okay, let's have 1,000 thresholds, right? So I only check this threshold and this threshold, right? Well, this is just a graphical example, right? So I lower the number of thresholds. I do not go through every threshold because I have many points and say, okay, this is sort of should be good enough, right? So I lose in precision, but I gain in speed, which is a common trade-off. And this is called bin, right? So everything between this threshold and this threshold is a bin. A bin is a basket, right? It's a sort of basket of, I don't know, points of X. So this is why it's called binning, all right? So this is another bin between this threshold. So you just lower the number of thresholds that you're gonna check. Is it clear? Good, very good. Okay, now oblivious decision trees. An oblivious decision tree is the one that has similar features or the same feature on one level, right? So here, for example, I have 4 features, and I say, okay, this is a root. I separate by one feature, but now in this, I have to use one feature. So I check a pair of thresholds every time, right? So I check every threshold for one feature, find the best, for another, find the best, and then I check, okay, which feature gives me the sum, the best sum of improvement, the best sum of information gain. And I choose it, and I choose the thresholds. So on every level, I choose just one feature. Right here, I have this one here. Oh, I'm finished, but still. Now, why? Any ideas?
Может оказывается быстрее.
Может
быстрее оказывается.
Можно
it's actually longer.
Можно
Takes
переиспользовать сортировку и все такое.
That is somewhat true, yeah. So this you can use tricks to make it faster, yeah, but not faster than just a common tree. Right? That's the problem. There are 2 reasons, main reason. One is again interpretability, right? If you first separate by one, then by the other, you sort of the way you decide for every data point is the same, right? In terms of features. Now, a second one is the number of feature you use is the number of layers, number of depth. So if I had 100 features and the tree with a depth of 4, I would still use just 4 features, right? So this is a way of feature selection built in, right? So I will only use the number of features that is equal to the number of layers of my trees or a depth of the tree. And pruning is easier as well, because if I prune and cut off some leaves, I cut off the feature as well. So when I prune, I also remove the whole feature. And if I don't have a feature, I don't need to calculate it, right? For the next point and stuff like that. Now, why is oblivious decision tree is very, very important? Because oblivious decision tree gave us a cat boost. Cat boost is one of the most popular libraries of gradient decision trees. And the first iteration right now, like everything is, you can do oblivious decision trees, you can do anything else. But the first iteration of cat boost, which by what then it was called MatrixNet and not a cat boost at all, MatrixNet, it was oblivious. And it was oblivious, yes, because it was quicker to calculate, but not in that modification. An oblivious decision tree is used in Yandex, which is the company and author of MatrixNet and CatBoost, was even more oblivious. It not only did it have the same feature, but it also had to have the same rule. Right? So here, for example, I have the same feature here and here, but the rules are different, right? Here it says it's more than 50, and here it says it's more than 30, right? Different rules. What Yandex did is they say the rules are the same. And this is why it's actually called MatrixNet, because now you can write the rules as binary, right? So now, for example, every data point is just characterized. So every rule is binary, right? Because it's the same, right, rule, you can define your point by binary string, right? And that binary string defines the root in the tree, right? Because all the rules are the same. And the operations with this matrix of binary string is much like you can optimize so many things there, right? Now, removing, for example, you can remove a layer from the middle, right? You can just say, okay, let's remove that and merge everything together, right? So now just the points are less than, right? So you can remove like whole chunks of features. And this is much more easy to calculate and sort of manipulate. So this is why it's called matrix, because it's now a matrix of rules and points, which is binary matrix. Very fast, you know, like binary matrix, very fast to calculate. But now, you know, with current processing power, like it sort of lost their value. I think it's still used in Yandex to this day because of just how many models they have to run every day. I think it's still the initial version of CatBoost is used. Maybe not. Haven't worked there for quite some time. Can ask next time. But the CatBoost that I used, like if you want to use CatBoost in your research project, you can actually say, okay, I want the oblivious decision tree, or I do not want the oblivious decision tree. I can want something else. Just a simple tree. So these are one type of strange trees, oblivious decision trees. Another strange type is fuzzy decision trees. Okay, now
можно еще вопрос вот по прошлым деревьям?
Yes.
Во-первых, там может быть такое, что на разных уровнях одна и та же фича.
Yes.
Окей. И еще вопрос, что вот здесь написано на слайде вот GAHP.
Well, in this particular case, you try to find if the person has diabetes or not. So this is glucose level, age, hypertension is the blood pressure, and pregnancy is, well, pregnancy. So you have your glucose level, but glucose level depends on the pregnancy and age, so stuff like that. So true, you have diabetes. False, you do not have diabetes. That's it. Now, okay, fuzzy decision trees. This is actually not a very informative picture, unfortunately, but let's say, okay, let's talk about it. Let's say you have a temperature, right? And you want to define whether it's cold or warm to put on shirts or to put on, you know, coat, right? You have to make a decision. Well, let's just not think about hot because we're in St. Petersburg, no hot weather here, just warm and cold. That's it. So you try and define shirts or winter coat, right? Now, what you can do is, okay, you can say, okay, I have a rule, right? If it's higher than that, then I put on a coat. It's warm. If it's lower, then it's cold. What fuzzy decision trees say is, they say, okay, if it's much higher than that, right, then it's warm. If it's much colder than that, then it's cold. But in the middle, it's sort of fuzzy, right? I'm not sure, cold, warm. So I have probability. So for example, for this level, I have a probability of it being warm, and I have a probability of it being cold. And they sum up to 1, right? So this is a linear function. So this, for example, is 0.8, and this is 0.2. Now, the thing is, and this is very important to understand, with this rule, nothing actually changes when you build a tree, right? Because if you go and look at all our information gain, right, nowhere it says that points have to be whole, right? So let's say I separate points, and for one point it's fuzzy, right? So all points fall into one bucket or one node or the other, and I say, okay, I have, I don't know, 0 points, I don't know, 2 points, and 4 points right here, and I have 0 points in this class, 5 points here, and 0 here. And the next point, 1 point, let's say from the third class, so this is 1 point, is fuzzy. So it's right on the threshold, right? Why can we say, okay, so let's say a 0.7 of this point goes here, and the 0.3 of this point goes here, right? So this becomes 4.3, and this becomes 0.7. But our equations still work, correct? Everything still basically works. Equations, impurities, calculations, errors, still works. Nothing changes. Why do we need fuzzy decision trees? Well, to be fuzzy, basically. Because let's say a point is on a threshold, right? Let's say it's 49.51, right? If you use a strict logic, right, you have to follow the rule. You still have to decide. Well, say it's this one, so it goes here, and the rest of decisions that you make for this point is based on that initial decision that you are actually kind of fuzzy about, right? So in this way, we can sort of hedge our bets. You can say, okay, there's a probability that this point belongs to this class, so it will to this node, to this branch. So let's send that probability here. So the half of the point will go here and end up in some class, and half of the point will go here and end up so on. But now you can add up, right? For this 1 point, you can add up probabilities from this leaf, and get a better decision. Because you do not follow a strict rule from the get-go, right? Because it was right on the threshold. So this is why we do fuzzy logic. Okay. That's it for me today. Any questions?
А можете еще, пожалуйста, вернуться к алгоритму, который был, и повторить в нем
Which
второй,
one?
который про ID3, C4, 5 и карт.
Sure.
Вот там второй пункт. Мы помечаем наше правило как majority классом, когда у нас вся информация на 0. Так?
Yeah, there is no information gain. Not information, but information gain. So an additional
По
information.
всем вариантам.
Yeah.
А такое вообще бывает?
Yeah, sure. Well, it's random. Let's say you divide, so sure. This is very easy to illustrate. Let's say 50-50, and then it separates 25-25, right? 25-25. Or 50-50, 0-0. No information gain there. And let's say it's random and you just try different thresholds, but whatever you do, it separates, right? It can go here and here 50-50.
Мне кажется, чтобы это по всем точкам было, должно быть совпадение точек.
Or that, yeah. It can be just all points are very close and you cannot go get a threshold. Or if you employ the binning technique, right? All points are in the same bin and you cannot do anything. So, yeah.
Еще вопрос, вот когда эта вся штука обучается, почему она вообще работает нормально? В смысле того, что вот когда мы пытаемся придумать более хорошее правило для высокого уровня, не для листа, а того, что где-то выше, оно же не сильно думает о том, что будет дальше в листах. В смысле, у нас тут нет никакого...
Yeah, it just works. So this just works.
Окей.
This is a better algorithm. There is a better and even better version that we're going to talk about next lecture, which actually employs a very, very hard method. You're gonna love, I think. I love it. So, but there is a mathematical sort of trying to find a way to approach an error that is far away from the standpoint of now. But yeah, we'll see how it goes.
И еще один вопрос. Вот дальше была deviance for regression. Она где используется? В смысле, вот это число, какая-то формула?
Or a regression tree, if you want to build a regression tree.
Ну, где в этом алгоритме она возникает? Эти правила, куда это хотите?
No, any regression task. Doesn't matter.
Сейчас нет, как она соотносится вот с тем, что у нас было до этого ЕГЭ и прочие штуки?
Those are for classification, and this one is for regression.
Мгм.
So it's different tasks. So they're not compared to each other. So
То есть это-
misclassification error, gene impurity, entropy, classification. This is all for classification, and deviance is for regression. So you do not compare them to each other.
Соответственно, вот deviance — это то, как мы считаем ошибку, когда мы решаем задачу регрессии.
Yes.
Все, спасибо.
Any other questions? Okay, then I pass the torch to Oleg, who is here. And thank you for your attention and have a nice practice.
Всем привет.
Спасибо.
Давайте начнем в 14:30.